Okay, good morning everyone. Welcome to another Learning at Lambert Labs session. And this week's presenter is Ramin. So I will hand over to Ramin.
Thanks, Aaron. So today we'll be looking at decentralized applications with Ethereum. But first, let's review the client-server model. So almost all applications follow this architecture. We have end users, clients, who use an application. And all the data has to flow through a central server. So it's the server who has the most authority in the network, which is why we call it the centralized network. So suppose Alice wants to send a message to Bob. The message has to go through the server and then go through Bob. They can't communicate directly. And where does the message get persisted? Probably in a database, again, owned by the server. So this is necessary because if the database were open, of course, Charlie would be able to actually come in and then spy on them or spy on their conversation, and we don't want that. But on the other hand, it establishes a requirement for trust, because we actually need to trust whoever owns the server to be able to use it. You wouldn't use some kind of server where you don't trust whoever owns it. They would actually be able to see your entire conversation, and if your conversation is important, that could cause issues. So what's the alternative? The alternative is a decentralized model. So here there would be no central authority. In a messaging application like WhatsApp, users would actually communicate with each other directly over the network. No one would have authority. So the question is, however, how should this be implemented? It's not quite straightforward. There are many ways to do this. One is just to have everyone be a server. That doesn't seem quite right, because then again, one person can shut someone else off, data can get lost. Someone can edit their side of the conversation to look different than your side of the conversation, and there's no single source of truth. So what exactly should we do here? And the answer is blockchain. So a blockchain is a chain of blocks. These blocks are records of transactions. Each block has a hash, which I've crudely drawn here, and each block references the previous block in the chain. And there's also an algorithm to check if the order of the blocks is correct based on the hashes. And because of how cryptographic hashes work, it's practically impossible to modify a block once it's been inserted into the blockchain. And that just becomes more difficult the longer the chain becomes. So what that means is we have a verifiable record that can't be tampered with because of the rules of logic, the rules of mathematics that govern it. Now, anyone who wants access to the blockchain will actually store it on their computer. So the blockchain can get really long, then people don't actually have to store all of it. They can store bits of it, and then some dedicated users will actually store the whole thing. If one person makes a transaction creating a new block, this will just propagate to all the other users who will update their blockchains. If for some reason there's a conflict, then there are rules to solve these conflicts. They're well defined for each kind of blockchain. So on a computer, you don't actually just store the blockchain as a file. You, in fact, store it within a virtual machine. That just makes it much more secure and ensures that if the file grows too large, it doesn't affect your computer. And so we actually have something that resembles a database that can't be messed with. But ideally, we would actually be able to write application code as well, because a server can not just store things in a database, it can also run code like Python code. We would want to do that with a blockchain. So how would we do that? The solution to that isn't Bitcoin, it's actually the Ethereum blockchain. So again, this is a chain of blocks. Each block stores a hash as well as a reference to the previous block. But it also stores a record of the transactions which lead to it being created. So here we have a bunch of transactions. And each transaction has a sender who signed the transaction. Within this signature, they also encode their private key so that when asked, they can verify their ownership of the transaction. And since cryptographic algorithms work one way, it's impossible to deduce the private key from the transaction. All this means is that other people can't pretend to be you. So it's secure. The transaction also stores the amount that was transferred in ethers. This is the currency that powers Ethereum. It's called an ether. And finally, and most importantly, the transaction stores a data string. So this data string is where things get interesting. So the Ethereum virtual machine in which the blockchain instance is stored is Turing complete. So in theory, it can run any computer program. So the transaction data can actually store a string which the Ethereum virtual machine will be able to execute as a computer program. And that's what we call a smart contract. That's the name for it. So most of the time, this will just be a very short string. It will just say, send this much money to this person. But sometimes it can be an entire computer program. But this actually causes a weakness because, like I said, no one owns this blockchain. But running long programs will cause computational cost. So we actually need a way to limit that. And the way we limit that is through this thing called gas. So gas represents sort of a unit of work. And all it means is that it costs you a lot of ethers if you want to submit something like an infinite loop, for example. It would just cost you a lot. So that discourages people from messing about or exploiting the computational resources of the entire network. So now we actually want to look at some practical examples of decentralized applications which are built on the top of the blockchain. And my favorite example is this one. Is Xbox, because Xbox realized that there was a better way to do financial reporting. So games are being developed really quickly, and the financial reporting technologies weren't able to keep up. They needed to ensure that royalty payments were made faster to programmers, musicians, special effects team members, other people, and they also needed to issue financial statements. And financial statements have something very important about them in that they should not be tampered with. There have been a lot of sort of corporate scandals where people have gone back and changed the books, sort of accounting scandals. We want to avoid all of that. How do we do that? We need an immutable record, blockchain. They also needed this to be accessible by users, again, blockchain, and they needed it to be as fast as possible. In fact, when they implemented the blockchain on Azure blockchain, they were able to bring down the time that it took to get financial records to their employees from 45 days down to just a minute or two. And again, this I think is one of the best applications ever. But let's look at a few others. So another one is this idea of an NFT marketplace. So again, images, videos are technological things. They can be represented on a blockchain. So in fact, ownership of them can be represented as such as well. So we can create a smart contract selling something to someone. So we have in the code, we can just write, sell this image to that person. The image can be represented, and then that person will actually be able to have a proof of ownership. They will be able to say, look at the blockchain, I own this image. There's an immutable record. These are becoming much, much more popular nowadays. And in fact, you can sell videos and music as well, although that technology is quite new. The way you would do that is you would just split up the song into a bunch of blocks. And then sell that to a person, which seems strange, but that's the direction this is sort of heading towards. A much older idea, of course, is social media, decentralized social media. I'm not sure about the value of this, but if we go, Ppath was supposed to be a competitor to Twitter, a decentralized one. In my opinion, doesn't work too great. But as you can see, all the data here, the dynamic data, it is not stored in a database. This all comes from a blockchain. Now, the images are hosted on S3, I believe, Amazon S3, but all the text that you're seeing is stored on a blockchain. Okay, so that's enough for examples, I think. It's best to actually develop one locally. So let's get on with an example. Now, we're obviously not going to deploy something to the Ethereum blockchain because I don't have the money for it, but we are actually going to create a private instance of the Ethereum blockchain within our computer using something called Ganache. So Ganache I have installed here, and I'm just going to open that up. It will take a bit of time, and hopefully it will open. Okay. And we're going to create a quick start Ethereum local workspace. And what this will do is hopefully populate 10 users within our blockchain and assign 100 ethers to each one of them. Okay, it does that. So we can see we have 10 accounts, and we only have, if we look at the blocks, only one block. This is the Genesis block. If we go into it, 0 gas was used to create it because, of course, it's completely fine to create this. It has a hash, but there's no hash that it points towards because it is the first one. So now we can actually create an application with this. And the way we'll do that is go here, and I've created the bare bones of sort of a front-end framework here. So my package.json, I have my application set up. I've already installed a light server, a nodemon just for the front end, and I've also installed this Truffle. Truffle is a framework, just like Django is for Python, just like Node.js is for JavaScript. Truffle is for decentralized applications. Web3 also helps it actually connect to the blockchain itself. So now we want to instantiate this. We'll do that by just writing Truffle init. That will hopefully work. And that will create a bunch of directories for us to use in creating our decentralized application. The first one that I'm going to look at is this Truffle Config Js file. What this does is it helps us connect to the blockchain. So we actually have to specify, just like you would with a database, say which port and which address it lives on. We do exactly the same thing here. So I'm just going to remove what I don't need. Actually, I need this because I want those configs. So here I'm just going to connect to localhost. Port 8545 is the standard Ethereum port, but Ganache actually uses port 7545 so that it doesn't conflict with 8545. So I'm just going to change this to 7. And then the network ID will just accept any network. That's perfectly fine. Mocha is for testing. I don't think we'll be doing that today. We don't have much time. And then for compilers, we're using the Solidity compiler. Solidity is the language in which smart contracts are usually written. It's similar to JavaScript, Python, C++ mixed together, essentially. Don't care about the version. Don't care about that. Do care about the optimizer. So this will just optimize our code. And I will set enabled to true. The runs parameter is kind of complicated. I'm not going to explain it. But essentially, there are different ways of optimizing. And this should take care of our configs. Great. So now we can actually add a contract. So here we see contracts, and there's a contract already created called the migrations contract. This allows the app to take care of migrations, and migrations have their own directory. So much like a database has migrations, a blockchain also has migrations. We take care of how the contract has changed the blockchain. We need to keep track of that. But now I'm going to actually create an application. The app that I want to create is sort of WhatsApp, except much, much simpler. So I want a text box, and I want users to be able to enter text. And then I want them to create records. So just a bunch of text appearing on a website. It's really simple. And probably not actually the best suited to a decentralized application. You should really be doing something else that suits it, such as cloud storage maybe. But we don't have time, so let's create something really simple. I'll create messenger.sol. And I'll just copy the sort of structure of this. I'll just call it messenger. The pragma just specifies the version of Solidity we're using. And I'll just remove all of this and start from a clean slate. So we actually want to store messages here. How would we do that? Well, first, it would actually be useful to know how many messages we have. So let's actually store an unsigned integer and call it the message count. And we'll set that to 0. We actually want this to be available outside of the contract. So let's make it public. Okay, I should do it. And then we're going to create a message object. So we'll create a struct for that. Again, really similar to C here. And we'll give that an ID as well. And we'll give that a body, which is a string, and we'll call it content. Okay. And now what we want to do is store messages. And we want to store them probably in something like a Python dictionary. Well, the sort of analogy here would be mapping, and we're mapping from an unsigned integer onto a message object or struct. We want this to be publicly accessible, and we'll call it messages. So now we have our messages stored. Hopefully that works. And we want to now create a function which allows us to actually add messages. So what we're going to do is go function, create message. And we're going to give it, of course, content. Let me just give this. This is the standard sort of convention that you would use for inputs. We want this to be public. And this will be our function. So in this function, we ideally want to, first of all, increment the message count, of course. So let's do that. And then we want to update this messages object to include our newly added message. So we're going to take the messages object. We're going to take a position message count. We're going to create a message. Message, again, takes an ID. So in this case, that will be the message count. It takes a string. In this case, will be content. And that is pretty much it, I believe. Okay, this is giving me an error. Yes, so here it says a data location must be memory or call data. This is just asking me where in the Ethereum virtual machine do you want to store this? Because by default, this doesn't get stored. I want to store it in memory so that it can be accessed down here, right here. Now, another thing that I actually want is whenever a message is created for an event to get emitted, so that my JavaScript code, which I'll later tie into this, knows that a message has been created. So for that, I'll create an event object. So I'll say event message created. And for this, let's do unsigned integer ID and a string content. That should be fine, I think. Yeah, okay. Semicolon, please go away. Yes, okay, good. Now we're going to actually also emit an event at the bottom here. So when we run mapping and we run function here, I want to also emit a message created event. That will help us greatly. So that will actually take a message content and it will take content. Sorry, message count and message and content. All right. Lastly, I also want to populate the blockchain when it is initialized. So that will happen in the constructor object. The constructor is, of course, public. And we will just create a message which says hello world. Okay, that should be, what's this? Okay, that's fine. This is our program completed. So again, all it does is it creates a contract called Messenger with which you could add messages to a blockchain. It's pretty simple, and that is pretty much it. So now I think I need to migrate this. And to do that, I need to first write a migration. So migration is actually pretty standard. I have never written a complicated migration for these kinds of applications before. So I'll just keep it simple. It's just messages, messenger.js. And I'll copy pretty much the same format that this migration has, which already exists. And I'll just change the name to messenger, messenger, and messenger. Okay, that is our migration sorted. Now we need to compile our code, this, and then migrate it. So let's do that. So I think it's Truffle compile. Wait for that to happen. Okay, it's compiling. Excellent. It's compiled. We see there's a build directory which has been added now. And if we scroll down to the migrations here, if we scroll down, we see we have bytecode. So this is actually the representation of the program in bytecode, which will run on the Ethereum virtual machine. And if you remember back to my talk on WebAssembly, hopefully you'll remember Emscripten, which is the compiler that's being used. Again, is compiling JavaScript to the bytecode of a virtual machine. So again, Emscripten showing up. Now we actually want to migrate. So we're going to run truffle migrate. And this will migrate our changes to the. Hopefully it will work. Okay, good, very good. And we see here that the final cost is about 0.01 ethers. And this, of course, not being the real price of ethers, this being local ethers. Otherwise, it would be very expensive. Now we can actually go to our blockchain and we see 2 new blocks have been created. So the first one corresponds to that contract called migration. So this isn't one that we actually care about. This is the one that we care about, which runs our messenger contract. So we can actually see that the block hash has been assigned gas used, gas limit, mined on. I click on this, which is the transaction. We see this huge bytecode. And this actually corresponds to the code in messenger.json where we saw the bytecode earlier. So this starts with 608, 608. And so does this, 608. The sender address is us. So remember, in the beginning, all the users were assigned 100 ethers. We expect 7EAE to now not have 100 ethers. They should have less. 7EAE has 99.99. Well, actually, a bit more than that ethers, but this only shows it to 2 decimal places. So what we have done here is shown that we've made a transaction, but we haven't actually looked at whether the code has been populated. So we'll do that now. And the way we can do that is just look in the shell. So we'll go Truffle shell, just like you would with a Django shell, a Flask shell, a Node shell, maybe not, a console, sorry, Truffle console. Yep. And in here, we can actually interact with objects. So we'll do that. So I'll go messages equals await messenger.deployed. And what this will do is bring me the messenger contract, if it exists. Okay, excellent. And now I can actually just pick out the first message, which should be hello world, because that's what I initialized it in the constructor. So I'll go messages.messages. One, please work. Okay, message. Hello world. There we go. This is the content. The ID is what we call a big number. It doesn't print well, but the content is correct. Hello world. And the way it knows that is, well, first of all, it could just decode this and then realize that the constructor is what it says it is. But on the other hand, what it's actually doing is looking at the blockchain. It's finding the corresponding block. It's looking at the transaction. And then it's finding out that hello world is in fact been entered into it. Okay, great. So that's how we can interact with it. But now, how do we actually write a full stack web application? The way we would actually do that is HTML JavaScript. And I've already written these files just because it takes too long to write an HTML or JavaScript file. What this does is it waits for the user to log in. You actually have to log in to use a decentralized application for security purposes. Because otherwise someone might steal your ether or whatever. And then what we have is an input, which is just a text box. And then at the bottom, we have, if we press enter on the text box, we have text records. Okay, the JavaScript is actually pretty simple, but it's a bit long. Most of it is standard. So here we just load Web3, which is the module that we require. Here we load the Ethereum account. Here we load the contract. So I'm using jQuery here, and I'm just loading messenger.json that allows it to interact with the blockchain and pick it out. We use Truffle contract, which is sort of a constructor that turns it into something that we can actually use. And then here it gets populated with the data from the blockchain. Create message, again, is just sort of an RPC call to allow us to actually use the create message function, which we specified in the Bitcoin, sorry, in the blockchain function, but it allows us to use it from JavaScript. And then render just renders the entire web page. Set loading does the same. And then on load, we just load the app. Okay, sure. Now we want to run this. So to do that, I will just run npm run dev. Okay, and that should hopefully opens up the page. Okay, great. Now this won't work, and the reason it doesn't work is I actually don't have an account configured. So if I go to the console, it will break, sure. And I will need to use this Chrome extension called Metamask. This just allows us to interact with blockchains from a browser, because the browser by default does not actually have any means of doing this. There are dApp browsers, decentralized application browsers. I'm not using one of those. I use Chrome. So let's just use this extension. What we'll need to do is actually import an account. So I don't need this account. I need to import an account. The account that I need to import is the one that made the transaction, so this guy. And I need to take its secure, its private key. Okay. And we're just going to go here again. And I'm going to import the private key. So I'll import account, paste private key, import. Okay. Now I want this guy, account 4, to actually be connected to this website. So hopefully that will work. Let's see. Connect. Okay, so it's now connected. Okay, I'm getting an error here. Cannot read property 0 of null. Okay, let's see. In promise type error, cannot read property 0 of null. Function array for each truffle contract. Anyways, so what we've actually done here is, okay, so no close 7545. Okay, now it should work, hopefully. Yes, okay, that was kind of scary. Okay, so now we actually have a text box here, and we can enter some text. So hello again, I'll hit enter. And now what will happen is we'll get a screen which will tell us to confirm. And here we just sign the blockchain. So we actually make a signature. I'll confirm. And that should work. And there we go. Hello again. So what we have here is a very simple application where we can type text. We hit enter. It shows up on the web page. And then if we go back to the blockchain, we actually have an additional block, which was just created just now. And that is how you create a very simple decentralized application on Ethereum blockchain. That's pretty much it from me. I'll hand over if you have any questions.
Thanks for that, Ramin. Really interesting. Yeah, I guess just a really quick question from me. The gas attribute of each block, what's the conversion of gas to ETH?
Yeah. So in the Ethereum white paper, there was a simple formula for it. I can't actually remember the formula right now, but it's in terms of sort of opcodes. So in the virtual machine, it knows what each code in that bytecode means. It can roughly guess what kind of program we're talking about. But yeah, I'm not an expert on that. But essentially, it's about how difficult of a computation the program is. So if you have an infinite while loop, there'll be infinite gas.
Nice one. Does anybody else have any questions?
Yeah, I just want to ask to clarify a bit about like what's the difference between, in this case, posting a message and creating a new block, and in another case, like actually writing application code. So at the very beginning, when you had the like the two new blocks, when you actually run the migrations, was that the app code? Yeah, I just want to kind of clarify that.
So when I run the migrations, this JSON here, this is just a representation of the bytecode, but it doesn't actually get written to the blockchain. So you don't actually need this. Anyone can interact with it now within the blockchain. So what they can do if they want to interact, for example, with the code that I just read, is they go to the block. This was the block. They go into the transaction. From this, the contract can get inferred. And then all you need to do is create a transaction for that contract. So you see here, it says create a contract address. All you need to do is within the Ethereum virtual machine, say, I want to create a transaction on that contract. And then what happens is that contract gets executed, but for you. So yeah, so anyone can now work with this contract. It's publicly available. Anyone can see it. There are ways to keep some security, some privacy in. So, for example, you could make it dependent upon your secret key. But yeah, that's pretty much it.
Okay.
Okay. Well, thank you again, Ramin, and yeah, thanks for listening, everyone.
Yeah, thanks.